Look at this one, a classification task. So here, you download some data, and this is MNIST. And what this is a famous data set which consists of handwritten digits written by American census takers. So they just wrote down these numbers, and therefore, it is a task. How do you recognize these numbers? And as you can see, sometimes they're clear, sometimes they aren't. The ones have different shapes and different tilts and so on. So you'd like to have a machine learning system that can read and sort these numbers into 10 categories. And your database has thousands of these with the correct labels. So you can train it on this database. You know what the right answer is, so you can tell if you're getting it right and train your model. So you make a training and testing set. You take the first 60,000 for the training set, and the testing set is the ones after 60,000, which is another 10,000. So that's as usual. Most of them are used to train, and then you have some that the model has never seen before to test it on to see if it really learned the underlying trend or if it just memorized your images, which is not as good. So then you make we're going to make a simplified classifier here. We're going to make a binary classifier. So instead of sorting into 10 categories, we're just going to do 5 or not 5. So 90% of them are not 5. So we make a variable for that. And now, so here's the training set. True is 5,400 and false is 54,000. True means it's 5 and false means it's not 5. And so here's the training set and here's the test set. A smaller number again, about 10 times as many false as true. So we can make a linear model, which goes like this. You feed in the input image. It has, I think, 28 by 28 pixels. And you just take each of those pixels and treat them as independent inputs into the machine learning model. And then you feed them all into a neuron, and the neuron does the calculation. This is incredibly primitive, and by the way, incredibly stupid, and not the way your eye works. It would be far better to pre-process the image to detect things like an edge. Like your eye looks at this, you say, well, this is the background, so ignore all of that. This is a line going that way. This is a line going that way. Cells in your retina close to the receptors do these kind of simple comparisons and then pass higher level signals up for processing in your brain. And you could make a computer vision model that does that, but we're not doing that here. We're making a much simpler model that just treats each pixel as independent information. And the thing to notice is it doesn't even know that these pixels are near to each other. I didn't even preserve the spatial location of the pixels. So it doesn't know that here I have a bunch of black things all next to each other tracing out a line. It's going to have to figure that out, and that's probably going to be a lot less effective than a multi-layer model that extracted meaningful symbols first.
So it's just taking the number, putting it into a bunch of pixels,
Yeah.
and seeing which pattern in the database it lines up with best.
Yes. Yeah, exactly. But anyway, it's simple to write this thing. You make a stochastic gradient descent classifier, and stochastic gradient descent works by you have a linear combination of all these things with parameters, and you just do a partial derivative. You have a loss function, which measures how wrong you are, and you measure how it changes in response to a small change in all these parameters, which is just partial differentiation on many variables. So you can predict what direction should lower the loss. And if you take a small step, the assumption that it's a straight line function will be true, and so you can take a small step and make the loss smaller and just take a lot of small steps. That's stochastic gradient descent, and it's one of the most common ways machine learning models work. So you set the thing up, it then trains, and it chose to train for 239 epochs. Now, I didn't tell it how many time steps to take, but what it did was, you see the loss here, 78.6, 77.6, 77.8. This is something you commonly do. You take small steps, and you just go step, 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 as long as it's getting better. And when it starts getting worse, then you stop. You appear to have hit the bottom. That seems to be a way to detect the bottom. As soon as it starts getting worse, you know you've pretty much hit the bottom. So we're done. It took 30 seconds to do it. And now we have some predictions. All right. And here's the actual right image. So it correctly predicted that the first one is indeed a 5, and the next two, which were a 0 and a 4, are false. So the first 3 predictions are correct. And now we can rate its accuracy. And so you see here, here's 3 accuracy. Now you're doing this with cross-validation. This is another way to do it, to test a model. You split the training data into 3 parts, and then you train it on 2 parts and test it on the 3rd part, and then you just shuffle them. So you train it 3 times on different 2/3 of the data and test it on the other 1/3, and here you get 95%, 96%, and 96% correct. That's cross-validation, and that works. That sounds good, although to be fair, it's not all that good because remember, 90% of the data is not 5. So if you just said false all the time, you'd be 90% correct. So being 95% correct is not as impressive as you might think. Let me check for comments in the Twitch. Okay, nothing new. All right. So then you can make confusion matrices, which is how you rate it. Here's the whole story. These are not 5s, correctly identified as not 5s, 50,000. And 5s, correctly identified as 5s, 3,000. But here's not 5s, incorrectly identified as 5s, and you see there's a lot of them. And here's 5s, incorrectly called not 5s. So this is the full representation of the accuracy of your model, and as you can see, it's not even. It's like the 5s, you have a certain percentage, 6 out of 35, 1/6 chance of missing a 5 and calling it a not 5, but the chance of calling a non-5 a 5 is much higher. So if you take the population of things it's labeled as a 5, it includes 1,800 non-5s with 3,500 5s, so certain areas where it's not that good. And there's various ways to measure this. True positives or true positives plus false positives, that's called precision. Recall is true positives or true positives plus false negatives. And there's a thing called the F1 score that compares those things. And the point is you just get a single number, and it's 1 if you're perfect, and it's lower if you're lower. And depending on your use case, you might want to maximize one of these measures of success more than another. Depends on what you're doing. And so you can actually play with the precision recall trade-off. What happens is the model just produces a signal, which is a floating point number that goes through a range, and you decide that a signal above a certain threshold you're going to call a 5, and a signal below that threshold you're going to call a non-5, and you can move that threshold. So you can adjust it. If you set the threshold very low, then you'll get recall better than precision. If you set it very high, you'll get recall less than precision. You're just choosing which errors you care about more. And so you can view the raw output here. You can see here's the raw output for various inputs. So this 5 gets a number of 2,000, the 0 gets minus 5,000, this 4 got a minus 13,000. And so if the threshold is 0, you call this a 5, and you call that a 5, and you call all these non-5. So the typical default threshold tends to be near 0, but you can make a graph of how it varies with threshold. And so you can see you make the threshold very low, you get high precision, but low recall. The crossover point is near 0. And if you get very high, this gets higher than that. And at some point, you get so high that almost nothing is ever called a 5, and so you have only a few 5s, so you start getting jaggedness in this number because you have a small denominator. That's the way to see how it works. Anyway, and then you can do multi-class classification. So they actually sort it into 10 categories. And if you do that, now each one of them is going to have to give you 10 values. So this one is really a 9. And here's the output of all the neurons. The chance that it's 0, 1, 2, 3, 4. And you can see the 9 is the biggest. It's 8, but 8 is pretty close at 6. And 7 is pretty close at 5. In fact, here's something. It looks like it got this one. It most thought this 9 was, I think, a 5. 0, 1, 2, 3, 4. Yeah, it thought it was a 5, actually. But that means it got the answer. I think that means it got it wrong. Anyway, here's the raw output of these neurons. And so you can now use classifiers. And if you want to classify it into 10 categories, you only have binary classifiers, so there are different ways to do it. One is to do it this way, 5 and not 5, 0 and not 0, 1 and not 1, and combine those. That's one way to do it. And then you can do train it in this model and get a mount of this. And then you can see how overfitting works. And you'll see this model that used these multi-stage classifiers seemed to get more correct. But in fact, here, it was much worse at the test set. It made 91 errors. This one only made 5 errors in the training set, which was a few thousand, I think. Out of 1,000, it only made 5 errors in the first 500 training images. That's what this is. So that sounds really good, but when you give it the test set, it makes 91 errors in the first 500 test images. So this is overfitting. It is doing very well on the training data, but not very good on the test data. So it's not learning the general phenomenon. So when you show it new images it's never seen before, it gets them right. It's instead memorizing the idiosyncrasies of your training data and not learning the actual job. So then you can do it with cross-validation, see how it looks. And then you can make a confusion matrix, which I think is worth seeing. This is the full way to print out the entire performance of your model. You have the true label from 0 through 9 and the predicted label from 0 through 9, and of course most of the time it gets it right, so you have these big numbers in the diagonal, but all these numbers on the off diagonal are different kinds of errors. And you can see the errors are not uniform at all. Like there is a high chance that something that's really a 9 will be seen as a 4, or really a 4 will be seen as a 9, which you can imagine is similar shape. Here's a 13. There's a high chance that something's really a 1 will be interpreted as an 8. I wouldn't have guessed that. I would imagine it's because you're putting the thing on the bottom and the hook on the right. So you see, there's certain errors are more likely than others. And this is the, rather than just one number like precision, this is the way to really rate the quality of your model in more detail. And you can be a percentage or a raw number. So anyway, those are important considerations, again, in the nuts and bolts of how machine learning models actually work. So I'm going to stop this